Okay, this is part 2 of chapter 8, and we are continuing this section of convergence and divergence of sequences. And now we introduce one theorem that is about the uniqueness of limit. Okay, so suppose AN is a convergent sequence. A convergent sequence means a sequence that converges to some real number. Okay, then the limit is unique. So this means there are no two unit limits. Okay, there are no two limits. If there exists a limit, then that is unique. So let's prove this. I mean, this sounds very trivial, but anyway, let's prove this. So suppose we have two limits. Okay, so let alpha and beta, which are real numbers, be the limits of this sequence. Okay, then take any positive epsilon. Okay, positive real number. Okay, this can be anything. Okay, however small or however large. Okay, so first of all, alpha is a limit. So limit of an is alpha. So this means for this epsilon, there exists some integer. Let's call it n prime. Some natural number such that for all natural numbers that are greater than this n prime, an minus alpha is less than epsilon. Okay. And similarly, since beta is also a limit of an, so this means there exists some natural number, let's call it n double prime, such that for all integers, all natural numbers, oh wait a minute, sorry, this should be if n is greater than or equal to n prime, then an minus alpha is less than epsilon, right? So in this case, if lowercase n is greater than n double prime, then an minus beta is less than epsilon. Okay, now let us define this capital N as the larger of n prime and n double prime. Okay, so max n prime, n double prime means the greater of the two. Okay, so the greater of the two is n. So let's see. Then alpha minus beta, if we take this difference, and alpha minus an plus an minus beta. So we add an and subtract an. So that means adding 0. So it doesn't change anything. So this is equal to this. And by using the triangle inequality, this is less than or equal to alpha minus an plus an minus beta. I think we should use Okay, so for any n greater than or equal to capital N, we have this. And since this lowercase n is greater than capital uppercase N, which is the greater of n prime or n double prime, so this one, this the first term is less than epsilon because of this, right? So here this n is certainly greater than or equal to n prime. And the second term is also greater than epsilon, less than epsilon because of this. This lowercase n is certainly greater than n double prime, greater than or equal to them. So this is epsilon plus epsilon, which is 2 epsilon. Okay, so this means we are taking epsilon as any positive real number. So this this inequality alpha minus beta modulus less than 2 epsilon means this quantity is less than any arbitrary positive number. Okay, arbitrary chosen positive number. So this means we have seen this argument before. So this indicates alpha is equal to beta. So therefore, this limit is unique. And that's the end of the proof. Next, let us define the notion of a bounded sequence. Bounded sequence. Okay, this is easy. So if there's a sequence, we can consider this as a set of real numbers also, right? So this is just a, if we ignore the order of the numbers, then it's just a set of real numbers. So if this set of real numbers is bounded above, then we say the corresponding sequence is bounded above. And if the set is bounded below, then the sequence is also bounded below. And if the set is bounded, that means bounded above and below, then the sequence is also bounded. And that's it. Now let us prove a little theorem. So any convergent sequence is bounded. Sequence is bounded. Okay, so let's prove this. Okay, suppose we have a sequence that is convergent. Let's say it converges to alpha. Okay, and let epsilon equal to 1. Okay, then for all, okay, so that is there exists, since because of the convergence, there exists a natural number n such that for all natural numbers, if this lowercase n is greater than or equal to uppercase n, then modulus of a n minus alpha is less than 1. Okay, in this case epsilon is 1. So this holds. Okay, now by the triangle inequality, inequality. Well, there are actually a few different versions of the triangle inequality, but we use this one here. an modulus minus alpha modulus is less than or equal to an minus alpha, which is less than 1. I mean, we're assuming this n is greater than or equal to n. Okay, so in this case, if we move this alpha to the rightmost side, we have an less than, actually this is strictly less than alpha plus 1. Now, this alpha is not infinity, so this means as far as this n index is greater than or equal to this capital N, then this sequence is bounded. Okay. Next, we show that this sequence must be bounded even if this n is less than capital N. Okay. For that, we define this constant, max of alpha plus 1 and a1, a2, and a3 up to a capital N minus 1. Okay, then obviously for n less than capital N, we have a n less than or equal to m. So that means when n is the index is less than capital N, it is bounded. So either case, so if this is greater, if this is less than, it's bounded either way. Therefore, this sequence is bounded. And we are done. Okay, but however, you should be careful that the converse is not true, So we said if convergent, if a sequence is convergent, then it is bounded. But not vice versa, okay? The converse doesn't hold. Why? To prove that, we just need one example. Okay, for example, if an is negative 1 to the power of n, then this is not a convergent sequence, but it is bounded. It can take only 1 or negative 1, so it is bounded, but it doesn't converge. Therefore, the converse of that theorem does not hold. Okay, the next theorem is a very famous and very useful theorem called Squeeze Theorem. So it's called Squeeze. And you'll see why it's called Squeeze Theorem. Squeeze Theorem. Okay, so here are the settings. Let's see. Suppose we have three sequences: an, and bn, and cn. Okay, these are sequences. Then suppose, well, we assume for all n natural numbers, we have an is less than or equal to bn, which is less than or equal to cn. And also, we assume that an converges. an converges and cn converges. So both converges to the same value, alpha. Okay? Then the limit of bn is also this same alpha. Okay, so this is a very useful theorem because suppose we want to find the limit of bn, some sequence bn, but it may be a little bit difficult to calculate the limit directly. But if we can come up with some other sequences like an and cn, which are known to converge to the same value, and also which squeezes bn from below and above, then we can know that the limit of n bn is also alpha. Okay, so let's prove it. So since an converges to alpha, there exists okay, let's say let suppose let epsilon be any positive real number. Okay, so since an converges to alpha, there exists some n, let's say n prime, which is a natural number, such that well, we just abbreviate the notation. So for any natural number greater than or equal to n prime, we have an minus alpha is less than epsilon. Okay, so this means in particular, this means negative epsilon less than an minus alpha, which is less than epsilon. Okay, we don't need this part, so let's just consider this part. And similarly, since Cn converges to alpha, so this means for there exists some natural number, let's call it n double prime, such that for all n greater than or equal to n double prime, Cn minus alpha is less than epsilon. Okay, so this means negative epsilon greater than Cn, less than Cn alpha, which is less than epsilon. So we don't need this part, so let's consider only this part. Okay, now from one of the assumptions here, this one, we have an less than or equal to bn less than or equal to cn, and by subtracting alpha from everything, we have this, and bn minus alpha less than or equal to cn minus alpha. But this an minus alpha is greater than negative epsilon, and this cn minus alpha is less than epsilon. So bn minus alpha, bn minus alpha, this one is between negative epsilon and positive epsilon. So this means bn minus alpha, its modulus is less than epsilon. So this shows, therefore, so this n is greater than, okay, I think I should say this n is greater than or equal to maximum, the greater of n prime and n double prime. Okay, so this holds for these n's. Okay, so if we define this max n prime and n double prime as n, then for any natural numbers greater than this n, we have this inequality. Therefore, bn also converges to alpha. And we're done. Okay, next let me explain the notion of subsequences. So for example, let an be a sequence. So we have a1, a2, a3, and so on. So these are all real numbers. Then let's see. If we pick some of these elements, we can define a subsequence, basically. So here's how we do it. First, let's pick a subset of, let's see, so let this nk be a sequence of natural numbers. Okay, so this is a subset of natural numbers. For example, n1, n2, n3, so these are a sequence, this is a sequence of natural numbers. Let's say, for example, n1 could be 2, okay, n2 could be 3. So we order this sequence in this set in the increasing order. This could be 5. So no, it's just any subset of natural numbers. Okay, then we can define, we can pick the elements of this original sequence that has the index corresponding to this sequence of natural numbers. For example, an1 could be is in this example, an1 could be element, and an2 in this case would be a3, and an3 in this case could be a5. So this subsequence an1, an2, an3 could be something like a2, a3, a5, and so on. So this sequence, this is a sequence of real numbers, obviously, and we say this is a subsequence of this original sequence. Okay, so we write a and k is a subsequence. No, this is just one of many subsequences of a n. Okay. So if you choose a different subset of natural numbers other than this, for example, you could choose n1 to be 1, n2 to be 11, and n3 to be like 21, and so on. You could define another subsequence like a1, a11, a21, and so on. So there are lots of subsequences possible. Next, we explain an important theorem about subsequence. Let's say an is a sequence of real numbers such that its limit is alpha. Okay, then let a and k be any subsequence of an. Then this also converges to, so in this case it's k. This also converges to alpha. Okay, look how we take this limit. You know, this in this subsequence, the real index is this k. Okay, so we take this k to infinity. Okay, so this should converge to the same value as the original sequence, parent sequence, if you would like. So let's prove this. Okay, let epsilon be any real number, any positive real number. . Okay, and since we're assuming that the sequence an converges to alpha, we have this following statement. So there exists some integer, some natural number n, such that for all natural number, we're assuming this n as a natural number. For all natural number that is greater than or equal to this capital N, an minus alpha is less than epsilon. Okay. Now, let's take a natural number, capital K, such that nk is greater than or equal to n. Okay, so this nk is a sequence of this nk is a sequence of natural numbers. So if we increase this k here, okay, nk. So if we increase this k, then this this can go to infinity. So it can get as large as anything. So at some point, if we take large enough natural number k, then it should be greater than this given natural number, capital N. Okay? So this means for any natural number k that is greater than or equal to this capital K, we have nk greater than or equal to n. Okay? Because all lowercase k, if it is greater than this capital, if it is greater than this capital K, then this nk should be greater than, this nk should be greater than or equal to, no, it's not equal to, it's greater actually, strictly greater. Oh, wait a minute. No, it's greater than or equal, yes. This n capital K, which is greater than n by definition here. Therefore, we have this inequality. Okay, so this means a n k minus alpha is less than epsilon. Okay, of course this k is this k. Okay, because this nk is greater than or equal to this capital N, so this should hold. So what we have seen is this: for any epsilon positive real number, we can show that this difference a and k minus alpha is less than epsilon if this k is greater than or equal to a certain natural number. So this means this limit exists. So a and k converges to alpha. So that's the end of the proof. Okay, the next theorem shows how to use subsequences to prove something interesting. Okay, here's the theorem. Okay, again, let an be a sequence that converges to alpha. Okay, then let's see. For some, let's see. If there is a real number and such that let's see, an greater than or equal to a holds for infinitely many n's. So suppose this is true. There is some real number such that the value of this sequence is greater than or equal to a for infinitely many indexes. Okay. Then, if this is true, then this limit alpha is greater than or equal to a. Okay, and similarly, if there is a real number such that an is less than or equal to a for infinitely many n. If this is true, then alpha, let's call it b instead of a. Then alpha is less than or equal to b. Okay. Okay, let's prove this, and we prove only the first part, and the second part should be very similar. Okay, here it goes. So, okay, first of all, let's define a subsequence. Let's call it a and k, which is defined by this condition: an, all elements of an, such that an is greater than or equal to a. Okay, so this a is the given a here. Okay, by this condition, so this holds for infinitely many n. So this means this subsequence consists of infinitely many elements. Okay, now we prove by contradiction. Okay, so suppose the limit alpha is less than a, then this should lead to a contradiction. And let epsilon be a minus alpha, which is positive, right? So because of this. Okay, then there is a natural number n such that for all natural numbers greater than or equal to this capital N, we have an minus alpha less than epsilon. Okay, so this means an minus alpha is less than epsilon, which in turn means an is less than alpha plus epsilon, but the definition of epsilon was a minus alpha. So this is equal to a. Okay, so an is necessarily less than a for all n that is greater than a certain value. But this is a contradiction because we have this subsequence which converges to alpha, right? And this contains infinitely many elements. So this cannot be true. No, so this says after a certain point, all elements of this sequence is less than alpha, less than a. So this is a contradiction. So that concludes the proof. The next theorem shows some basic properties of convergent sequences. So let an be a sequence that converges to alpha. And Bn is another sequence that converges to beta. So these are assumptions. Then we have the following. First, limit of Kan is K alpha, where k is a constant. Okay, and second, the limit of a sum is the sum of limits. Okay. Maybe I should write in this way. Limit an plus limit of bn, which is alpha plus beta. Okay. And 3, the limit of product is the product of limits. Okay, so that is alpha beta. And fourth, the ratio of limits ratio of this limit is the ratio of limits. Let's see. So this is an over limit of bn. That is alpha over beta. But given that beta is non-zero, of course. If beta is 0, then this is undefined. Okay, so if you look at the first two, this and this shows that the operation of limit, taking limits, is a linear operation. Right? So this is just like linearity. So this should be written as limit of a n. Okay. So if you multiply by a constant or scalar, then it is just a scalar multiplication of the limit. And if you add two sequences, then take the limit, then it is the limits of the sum of two limits. So this is exactly according to the definition of linear operation. Okay. And also, if you look at compare 1 and 3, this case 1 is actually a special case of part 3, where an or bn, either of them is a constant. Okay, so if, for example, an, let's say bn is a constant, it doesn't depend on any index, then this third case is reduced to the first case. Okay. Well, anyway, let's prove this. So first of all, since an converges to alpha and bn converges to beta, we have the following. Let epsilon be a positive real number. So this can be anything. Okay. Then there exists some natural number such that for all natural number greater than that n1, we have an minus alpha less than epsilon. And also there exists some natural number, let's call it n2, such that for all natural number greater than n2, we have bn minus beta modulus is less than epsilon. Okay, so these come from the assumption. Now we skip part 1 because it's part of, it's just a special case of part 3. So let's prove part 2 first. So let's define n as the maximum of n1 and n2. So that means the bigger of these two is defined to be n. Okay, so for all natural numbers greater than n, we have both an minus alpha less than epsilon and bn minus beta less than epsilon. Okay, now let's see. We want to show that this an plus bn minus alpha plus beta, we want to show this is less than some arbitrarily chosen positive number. Okay, so anyway, so this is equal to, so if you move alpha here, beta here, then we have an minus alpha plus bn minus beta. And by the triangle inequality, this is less than or equal to an minus alpha plus bn minus beta. Okay, but by the given condition, this and this, these are less than epsilon. This is less than epsilon, and this is less than epsilon. So that is, in total, it is less than 2 epsilon. Okay, but this 2 epsilon can be any positive real number because this epsilon is any positive real number. Therefore, this means an plus bn converges to alpha plus beta. Okay, done. Okay, so that's part 2, and let's prove part 3. For part 3, we use previous theorem. So any convergent sequence is bounded. Okay, so we can convergent sequences are bounded. So therefore, there is some positive number such that an is less than m and bn is less than m. Right? It's because they are bounded. From the previous theorem, we know that since an and bn are converge to alpha and beta respectively, so that means this, of course, this holds for infinitely many n's. Okay, so therefore alpha modulus is less than m and beta modulus is less than m. Okay, I think so far it's easy to understand. Now let's show that alpha n not alpha n, it's a n bn converges to alpha and beta. So we want to show this is less than some arbitrarily chosen positive real number. Okay, to do that, first we do this: an bn and minus an times beta and plus an times beta. So we subtract and add the same thing. So that is just 0. So it doesn't change anything. And split this modulus into 2 parts using the triangle inequality. So that will be an. Well, we also factorize by an, so that's bn minus beta modulus plus, and the second one we can factorize by beta, so that will be an minus alpha and beta. Okay, but now the modulus of a product is the product of modulus. So this is equal to an modulus times bn minus beta, and an minus alpha beta. And now we can use these bounds. Okay, so an is less than or equal to m. So this is less than or equal to m. And bn minus beta, this one is less than epsilon. Okay. Oh, actually, this should be strictly less than, because this is strictly less than. And similarly, this is strictly less than epsilon, and this beta is less than or equal to m. Well, anyway, we have this. So that is equal to 2m epsilon. Now, this can be any positive real number. This m is some fixed number, but epsilon can be any positive real number, so it can be very small. So this means this is equal to this. Therefore, an bn converges to alpha beta. Okay. To prove part 4, part 4 was this. We should be a little bit careful because it is given that beta is not 0, but it may happen that sum of bn may be 0. Okay, we have to avoid carefully such a case. But fortunately, because beta, which is the limit of bn, is non-zero, we can prove that there is some natural number such that for all natural numbers greater than or equal to this capital N, bn is non-zero. Okay, so after some point, bn cannot be 0. Otherwise, bn does not converge to beta, which is non-zero. Okay, let's show this. Okay, first of all, since beta is non-zero, we have beta modulus is positive. So, and there exists, so first we want to show this. So there exists some natural number such that for any natural number greater than or equal to this capital N, we have bn minus beta less than or equal to less than 1/2 of beta modulus. Okay, usually we write here an epsilon, but instead of epsilon we can write any positive number. So here we happen to use half beta modulus. Okay, so now we can use the triangle inequality. Okay, by the triangle inequality, we have minus beta modulus minus bn is less than or equal to bn minus beta. It's opposite. Beta minus bn, which is less than half beta. Okay, so this means, so looking at this and this, we have bn greater than, let's see, beta minus half beta, which is half beta, which is positive. Okay, so this means for any natural numbers greater than a certain value, bn is non-zero. Okay. So for n greater than capital N, we define a new sequence Cn, which is 1 over Bn. This is possible because Bn is guaranteed to be non-zero. Okay, then Cn converges to just write. Then Cn converges to 1 over beta. Okay, you should verify this. How can you say this? If we define Cn by this, Cn converges to this. Okay, so if this is the case, then by part 3, we have a limit of an over bn as limit of an times Cn, which is alpha times 1 over beta, which is alpha over beta. And we are done. The only thing that is still unclear is this part, and I leave this as an exercise. So if you define this, then you should have this. Okay, try to prove this. Okay, next we study monotone sequences and Cauchy sequences. In general, it is quite difficult to find limits of a sequence, but if certain conditions are met, then we can know that we can know whether a sequence converges or not without knowing the limit. Okay, so those conditions are include monotone sequences and Cauchy sequences. So let's move on. So here's first definition. Let A and be a sequence. And if we have this, so it's A1 is less than or equal to A2, and which is less than or equal to A3, which is less than or equal to A4, and so on. So in other words, it only increases or stays the same. So an in general is less than or equal to an plus 1, and so on. So to summarize this, for all natural numbers, we have an is less than or equal to an plus 1. So then we say this is a monotone increasing sequence. A monotone increasing sequence, or to be more strict, monotone non-decreasing sequence, because this includes equality here. So it may stay the same. So it's not, in that case, it's not really increasing, but it stays the same. But still, it's not decreasing. So we can say monotone non-decreasing or monotone increasing. And similarly, if we have a sequence like an is greater than or equal to A2, which is greater than or equal to A3, and so on. So in this case, we have we say this an is monotone decreasing sequence. Monotone decreasing, or monotone non-increasing. Okay. Let's see an interesting little example. Let's see. So here's example. Let us define a sequence by this. A1 is 2. And an plus 1 is defined by 1/2 an plus 2 over an, where n is 1, 2, 3, and so on. Okay, so this is the initial value, and the next value is determined by the previous value. Okay, then you should try to prove this. First, for all natural numbers n, an is greater than or equal to square root of 2. Okay. Certainly this one, a1 is 2, so it's greater than or equal to square root of 2, which is 1.4, and so on. And second, this sequence is monotone decreasing. So it never increases, it just decreases. And 3, the limit of this sequence is actually the square root of 2. Okay, so you can, for example, you can experiment this by writing a computer program. This is a very simple calculation. And maybe you can even use Excel or Google Sheets or whatever, spreadsheet applications to calculate some of these values. And here are the calculated values. So a1 is 2 by definition, and a2 is 1/2 a1, 2 over a1. So that is 2 plus 2 over 2, which is 3/2, which is 1.5. And if you continue this calculation, you should have a3 is 1.41666, and 6 goes on forever. And a4 should be, let's see, 1.41421568, and so on. And a5 is 1.41421356, and so on. So as you can see, this gets closer to square root of 2. By the way, square root of 2 is, as far as I can remember, that's hitoyo, hitoyo ni hitomigoro. So this is very, so 114411442211335556. Wow, a5 is already very similar to 2, up to 1, 2, 3, 4, 5, 6, 7, 8 digits. Oh, 9 digits maybe. Wow, maybe more. That's very impressive. Anyway, try to prove these 3 points. Okay, what you should observe in this example is this. First of all, this is bounded. Okay, bounded below. Okay, here. So it can never get less than square root of 2. And it is monotone decreasing. Okay, it is bounded below and monotone decreasing. So that means, so if you take n and take an, then it's always greater than or equal to square root of 2, and it is not increasing, so it's monotone decreasing. Then it converges to square root of 2. So we can say if it is bounded below and it is monotone decreasing, it converges to some value. And in fact, this result can be generalized to any sequence. Okay, so this is a theorem called monotone convergence theorem. Monotone convergence theorem, and which says any monotone, any bounded, okay, this is important, bounded monotone sequence converges. Okay. By the way, if we just say bounded, it means bounded both above and below. And if we just say monotone sequence, it means either monotone increasing or monotone decreasing. Okay, anyway, so let's prove this. So first, let's prove this for monotone increasing sequence. So suppose an is a bounded monotone increasing sequence. Okay, then since it's bounded, there is a supremum. Okay, so supremum of this set of real numbers, sequence viewed as a set of real numbers has a supremum, okay, exists. And this is the property of the continuity of real numbers, right? And okay, so for any epsilon which is positive, alpha minus epsilon is not an upper bound. Because the definition of this supremum is the least upper bound. So anything that is less than alpha cannot be an upper bound. Okay, so this alpha minus epsilon, however small this epsilon is, it cannot be an upper bound. Okay, so this means there exists a natural number n such that let's see, alpha minus epsilon is less than a n. Okay, because this alpha minus epsilon is not an upper bound, there is some element of this sequence that is greater than this value. Okay, that's what it means to be not upper bound. So, and also here we are assuming that the sequence is monotone increasing. So this means for all natural numbers greater than or equal to this capital N, we have alpha minus epsilon is greater than a n, which is greater than or equal to a lowercase n. Okay, so that's one thing. But alpha is a supremum. So that means for any n, an is less than or equal to alpha, because alpha is the supremum. And if we add epsilon to alpha, that is greater than alpha, of course, because epsilon is a positive value. So therefore, we have this inequality on one hand and this inequality on the other hand. So that is alpha minus epsilon is less than an, which is less than alpha plus epsilon. Okay, remember we are considering only these natural numbers. Therefore, so that means an minus alpha is less than epsilon. So this epsilon is arbitrary. Okay, but epsilon is arbitrary. So it can be any value as long as it's positive. Okay, so for any positive epsilon, there exists some natural number n such that for all natural numbers greater than or equal to the capital N, we have this inequality. So that means nothing but an converges to alpha. Okay, so the proof is done. In the case of bounded monotone increasing sequence. And we can also show that same thing for bounded decreasing sequence in a similar manner, which is left as an exercise. Okay, so we're done. Alright, next we define a very important notion of Cauchy sequence. So here's the definition. This definition is a little bit involved. So Cauchy sequence. Again, don't say Cauchy. No, this is not Cauchy. It's Cauchy. Cauchy. He's a Frenchman. Okay, anyway, so here's a sequence again. So we say this is a Cauchy sequence, or simply just Cauchy. If the following condition is satisfied. So that is, for any positive real number epsilon, there exists a natural number capital N such that for all natural numbers k and l, if k and l are both greater than or equal to the capital N, then the difference between a k and a l is less than epsilon. Okay, so if this holds, then we say this sequence an is a Cauchy sequence, or just the sequence is Cauchy. Okay, so what does it mean? So let's plot this sequence. For example, an, let's say this is like this. So let's pick any positive real number epsilon for whatever that value is. If we take a large enough natural number n, then beyond that point, the difference between any two elements, let's say this is k and this is l, okay, the difference between any two elements beyond n is always less than epsilon. Okay, so epsilon. So if you take a little bit smaller epsilon, let's say this much, then if you take larger value of n, then again the difference between any two elements beyond that value is always less than epsilon. So if you can choose some natural number like this, if you can always choose something like this, then this sequence is said to be Cauchy. Okay, this concept is important for the following reasons. For the reasons we will show later in later theorems. And the first important result involving Cauchy sequences is this theorem. Okay, any convergent sequence is a Cauchy sequence. Is a Cauchy sequence. So this means if an converges, then this an is Cauchy, is a Cauchy sequence. Okay, so let's prove this. So suppose an is a convergent sequence, so and the limit is alpha. Okay, so here's the assumption. Okay, so let's assume this. Then this means for any positive real number epsilon, there exists some natural number n such that for all natural number, okay, in this case, let's say for any natural number k and l, such that for any natural numbers k and l, if k is k and l are both greater than or equal to this capital N, then since it's a convergent sequence, ak minus alpha is less than epsilon, and al minus alpha is less than epsilon. Okay, so this is a little bit of improvisation of the definition of convergent sequence. But this k and l they are just symbols, so it can be anything like m and l or m and n and so on. But anyway, so what we want to show is that this sequence is actually a Cauchy sequence. To show that, we need to show ak minus al is less than any some arbitrarily chosen positive real number. So here it is. So this is minus alpha plus alpha and al actually. And so applying the triangle inequality, this is less than or equal to ak minus alpha plus alpha minus al. Okay, but according to this assumption, it's a convergent sequence. So both of these terms are less than epsilon. So that's in total ak minus al their difference is less than 2 epsilon. And of course 2 epsilon is arbitrary positive real number. Is arbitrary. Is an arbitrary positive real number, because epsilon is okay. Therefore so this satisfies the condition of the Cauchy sequence, right? So for any epsilon, there exists some natural number such that for any natural number kl greater than that capital N, now we have ak minus al, that their difference is less than some arbitrary positive real number. So therefore this sequence is Cauchy sequence, and we are done. Now, what's conspicuous about real numbers is that the converse of this theorem is also true. So here it is, theorem. Any Cauchy sequence is a convergent sequence. Any Cauchy sequence converges. Okay, but the proof of this is beyond the scope of this lecture. So if you're interested, please find it somewhere else. Okay, so this means this. So a sequence that is Cauchy is a convergent sequence. So if this sequence converges, then it is Cauchy, and vice versa. So that means AN is a convergent sequence if and only if it is a Cauchy sequence. Okay. Actually, this fact comes from the continuity of real numbers. Okay. For example, in a previous example, let's see, where is it? Oh, this one. So if we define a sequence like this, all the terms of this sequence is a rational number, right? A1 is a rational number, and A2 is a rational number because it's defined by this, just that rational number plus 2 over that rational number, which is a rational number. So if you add them, it's a rational number. If you divide them by 2, it's a rational number. So every term in this sequence is a rational number. Okay? And this is actually a Cauchy sequence. Now, as you've seen, this is a convergent sequence. So any convergent sequence is a Cauchy sequence. Okay? And this is a Cauchy sequence. And so it is convergent. But we have to consider everything within real numbers. Okay? But if we consider only rational numbers, okay, so every term of this sequence is a rational number. Okay, it's an element of rational number. And still, this is a Cauchy sequence, okay? However, if you stay within the set of rational numbers, then this does not have limit within rational numbers because its limit is square root of 2, which is irrational. Right? So as long as you consider only up to rational numbers, then the converse of that theorem, the Cauchy sequence, may not be a convergent sequence if you consider only rational numbers. This theorem is true only if we consider the set of real numbers. Okay? In fact, real numbers can be defined in this way. So every Cauchy sequence converges within that set, and that set is defined to be the set of real numbers. Okay. Okay, next I just introduce one theorem without proof for later reference. That is called Bolzano maybe, and Weierstrass theorem. Okay, here it is. So let AN be a sequence such that AN is within the closed interval between C and D for all n. Okay, then there exists a subsequence ANK. Okay, subsequence. subsequence of an such that such that its limit is an k, such that it converges to some value between c and d. I mean, we have to say this converges. Converges, and the limit exists within this closed interval. The proof of this is not beyond the scope of this lecture, but it's quite tedious, so I just skip it. And if you're interested, please find it out somewhere. And this is a very famous theorem, so I think you can find the proof somewhere. Alright, next we look at this constant again, which is Napier's constant or Euler's number. And we have studied this before when we studied complex number. This constant was introduced as the value of this function exp when its argument is 1. And this function was defined to be the inverse function of the natural logarithm. Right, so this was the inverse of this function. Here we define this constant by a different method. So namely, we define this as this limit of a sequence 1 plus 1 over n to the power of n. So it is another matter to show that this constant defined here is actually the same as the constant defined here, which we do not do here. But anyway, we try to show that this converges to somewhere between 2 and 3. So this converges to somewhere between 2 and 3. Okay? In fact, the value of this constant is something like 2.718 or so, I guess, and 28 and so on. So that's what we are going to show now. Okay, to show that this sequence defined by this converges with okay, first let's define this. Okay, an is 1 plus 1 over n to the power of n. Okay, we want to show this sequence converges. And first, we show that this sequence here is monotone increasing. Okay. So let's prove this. First, we want to show that an is less than an plus 1 for all n. So that's what we want to show. Okay, first of all, let's apply the binomial theorem to this term. So 1 plus 1 over n to the power of n. So if you apply binomial theorem, what was it? Let's see. That's something like k from 0 to n, and n choose k, and here 1 to the power of k, and wait a minute, is that okay? I think I should instead use 1 over n to the power of k times 1. to the power of n minus k, which is just 1. So we can ignore this. So this is something like k from 0 to infinity, 1 over k factorial, and the rest. The remaining part we put as sk. Okay. So here sk is, so that's the remaining part of the factorial divided by n to the power of k. So that is, let's see, that should be n minus 1, n minus 2, and so on, down to, let's see, n minus k plus 1 over n to the power of k. Okay, so let's split this into, let's see, so this n, and divided by one of these n's, n minus 1, n minus 2, n, and so on, down to n minus k plus 1 over n. You know, there are k factors in the numerator, right? So n, so this n is n minus 0, n minus 1, n minus 2, so n minus k, okay, n minus k plus 1 is n minus k minus 1. So this thing, minus k minus 1, varies from 0 to k minus 1. So there are k terms, k factors in the numerator. So we can split everything into the product of k factors. Okay, so this in the denominator we have n to the power of k. So it's a multiplication of n k times, right? So we can split like this. So this becomes, the first term is 1, the second term is 1 minus 1 over n, the third term is 1 minus 1 minus 2 over n, and so on, down to 1 minus k minus 1 over n. Okay. Then let's see. Then we do the same thing for a n plus 1. Okay, so this will be the binomial expansion from k equal to 0 to n plus 1. So similarly, we have some factor over k factorial, where tk here is 1 times 1 over n plus 1 times 1 minus 2 n plus 1 and 1 minus, let's see, n k minus 1 n plus 1. Okay. So, but for each I 1 to up to k minus 1, we have this inequality, 1 minus I over k is less than 1 minus I over n plus 1. Sorry, this is not k, this should be n, I guess. N, right? Because of course n is less than n plus 1, so 1 over n is greater than 1 over n plus 1. And if you put negative sign here, we have this. And then add 1 to both sides, then we have this. Okay, multiplied by any I between 1 and k minus 1. Then we have this, right? So this means also there are actually k terms here, k factors in this product. And of course, there are k factors in this product, k factors. So there are same number of factors in each sk and tk. But for each factor, we have this inequality. Therefore, sk is always less than tk for k equal to 1 up to k minus 1. Okay, so that means for n greater than or equal to 1, we have a n which is equal to this binomial expansion sk over k factorial, which is less than this summation n. Okay, be careful, this is n, it's not n plus 1 yet. Okay, tk over k factorial, and this is of course less than. So if you add one more term to the right, one more positive term to the right, tn plus 1 and n plus 1 factorial. And then this is the last term is equal to a n plus 1. Therefore, for any n natural number, an is less than an plus 1. So we are done. That is this sequence an defined by this is monotone increasing. Actually, it is strictly increasing. Next, we show this lemma. That is, this sequence is bounded between 2 and 3. N to the power of n is less than 3. Okay, so okay, of course this is a n. Okay, now let's prove this. First of all, a1 is 1 plus 1 over 1 to the power of 1, which is 2. Okay, so the first term is 2, and we have just shown that this sequence is monotone increasing. So every other term is greater than 2. Okay, so a2, a3, and so on, they are all other greater than 2. So since an is monotone increasing, we have an greater than or equal to 2 for all natural numbers n. Now let's see. So using the same sk, using sk defined in the previous proof, in the above proof. So we had, remember, this is 1 times 1 minus 1 over n times 1 minus 2 over n times and so on, and up to 1 minus k minus 1 over n. Okay, and you should see that this is less than 1. Why? Because this term is less than 1 and it's positive. It's 1 minus some small number, which is, this 1 over n is clearly less than 1, so this should be positive. and less than 1. And same for this. It should be positive and less than 1. And actually it applies to everything here. Every factor is less than 1 and positive. Therefore, the product of numbers less than 1 is less than 1. So this is less than 1. Okay, so that's for all k from 1 to n minus 1. Okay, and so we have an is equal to 1 plus 1 plus s2 over 2 factorial and s3 over 3 factorial and so on up to n over n factorial. Okay, so this is less than or equal to 1 plus 1 plus, so s2 is less than 1, so this is, so if we replace this s2 part to 1, this is greater than, this one is greater than s2, and 1 3 factorial and 1 over n factorial. Okay. By the way, when we put k equal to n, then we have n minus 1 here, so it's still less than 1. Okay, now let's see this n factorial. N factorial by definition is 1 times 2 times 3 times and so on up to n. But this is greater than 1 times 2 times 2 times 2 times 2 times 2. Okay, so we replace this 3 by 2, which is, 2 is smaller than 3, and 4, we replace this 4 with 2, so everything above 2 is replaced with 2. So we have this inequality. Okay, and this is, there are n minus 1, so there are in total n minus 1 2's. So this is equal to 2 to the power of n minus 1. For, of course, this n should be greater than or equal to 3. Because we need at least 3 here. So n should be greater than or equal to 3. Okay, then using this, so this n factorial appears here, right? So this an is less than or equal to 1 plus, okay, consider this part, and 1 plus 2 factorial plus 3 factorial plus 1 over 3 factorial and 1 over n factorial. Okay, then using this inequality, this is less than or equal to, actually strictly less than 1 plus 1 plus 2. So 2 factorial is greater than 2, and 3 factorial is greater than 2 to the power of 2 to the power of 2. Okay, so that's n minus 1. So, and up to 1 over 2 to the power of n minus 1. Okay, now I don't show the details, but this summation here, 1 plus 1 half plus 1 over 2 squared, 1 over 2 cubed, up to 1 over 2 to the power of n minus 1, this is equal to this, 2 minus 1 over 2 to the power of n minus 2. Okay, so this is 1 plus 2 minus some small number. So this is clearly less than 3. Okay, so that was to be proved. Okay, so the first term is 2, and second, the sequence is monotone increasing, and last, any term an is less than 3. So therefore, for all a natural number n, an is between 2 and 3, including 2, not including 3. And we know that already, that any bounded monotone sequence is a converging sequence. It's a convergent sequence. Therefore, this sequence, our sequence here defined by this term, converges somewhere between 2 and 3. And in fact, its value is 2.71828 and so on. So that's another way to define Napier's constant.